Yeah, sorry. Do everything on Zoom. So there are no students online and only two here. So I wonder something wrong. Let me check. So should we be in a different room? Did somebody check rooms? You checked it? Yeah. Okay. Well, we will have a recording. Hello. So is there some deadline today? Just because I'm curious, there is no one online, but I had a lot of
I don't know
trouble.
about AI.
Yeah?
Maybe they have some deadline on program engineering. I don't know.
Yeah.
Maybe it's
Yeah. Tomorrow or something, a session starts and people already left.
Right.
Okay.
But I don't think there are courses which ends this module and I don't think there are any exams. So
So people go traveling or
Ah.
dacha or whatever. Yeah.
Yeah, session becomes holiday.
Yeah. Or for work, they suddenly have deadlines and work because they postpone. Okay, whatever. So, okay. So already more
Less
people.
people, less questions.
Yeah, but today is a completely standard lecture, like many people teach it. So, and we just go through chapter 8 of Sipser book. Uh, well, except, it's space complexity. So, I mean, most of chapter 8, I think 1.3 is about some infeasible problem with automata. We don't do anything with automata. And we had to finish one thing from previous lecture. So I just gonna change the view. Yeah, just in Zoom. Okay. So from previous lecture, okay, let's write the goal. So we will prove that circuit sat. Also, there were no good markers. So is it readable?
Maybe have one. I hope so.
So I was writing here.
Yeah, I have a good marker.
Even a black one. Really cool. So circuit sat reduces to 3 sat from previous lecture. And then we will speak about PSPACE. So I will directed reachability problem. So given a graph and 2 nodes, can you find the path? Directed graph, can you find a path that reaches? And so this problem is in log space, in space squared of log. Log squared n for graphs of n nodes. And then we will prove that PSPACE equals NPSPACE. Then we will define TQBF and then prove that it's PSPACE complete. And then we study generalized geography. It's a game, and also prove it's PSPACE complete. Summarizing and generalized geography. So these are the plan. So it's kind of ambitious plan. But let's try because we lost 3 lectures in the beginning. So okay. Last year, I also dropped a lecture, so drop one more, and then we went fast to recover one. Okay, so first, let's remember what the circuit's at. Input is a circuit. So, okay, I'm not going to write it. You remember. So we had given a circuit question. Can we find input so that circuit evaluates to 1? And then 3 sat. So you remember this one. So let so given Boolean formula, can we find values so that it evaluates to 1? Okay. And so plan of reduction. So given a circuit, we need to come up with a formula. So let me draw some circuit and then do everything with an example. X1, X2, and something like this. It's kind of stupid. Here, let's put a negation gate. Or let's do the XOR circuit. So here is negation gate. And so now we have to transform this to a formula. So number of variables of formula will be the number of nodes in this graph. So we will have a variable for every input and for every gate. So let us call this, these other gates, let's call them Y1, Y2, Y3, Y4, and Y5. And so the plan of the formula is to, so 3-sat formula, remember, it consists out of clauses of at most 3 elements. And so in every clause, we can enforce something to be true. And so we just have to, so we just have to, so the variables of the Boolean formula, they provide first the input that makes the circuit evaluate to 1, plus the values of all the nodes in correct evaluation. And formula will just check whether output node is 1 and whether all computations inside the circuit are correct. So formula will be of the form Y5. And so let me write it informally. What is the formula? So it is and all the Y's are correct. So Y1 equals not X1. And then similar for Y2. Y3 is equal to Y2 or X1. Y2, Y3 equals to Y2 or X1. Okay, and now we know that every such constraint, it is a function from a certain number of variables. So here we have a constraint, a function of 2 variables. Here a function of 3 variables. We can write each function as CNF. Each function evaluates. So this is the function that evaluates to 1 if Y3 is correct value given Y2 and Y1. Mm-hmm. And so we know we can write this as a CNF, and so we have more clauses here. Sorry. Yeah, we saw it was a 3CNF itself, and so we take the conjunction of everything. Yeah. So yes, that's it, the reduction. So I can do it more explicitly, but that's yeah. So you remember the construction. So let's just skip all the rest. Okay. So this is done. And now we have completely proven that 3-sat is NP complete, because previous lecture we proved that circuit sat is NP complete. So there is a famous teacher, Eric de Man, he calls it grandmother of all NP complete problems, because almost always the reduction goes to 3-sat. And if it's not 3-sat, maybe a circuit sat if you have a circuit. Okay. So now we go to this problem. So first I need to define space classes when the space bound is smaller than linear. But I already mentioned how it's done. because the input takes linear space, so we need to do something special with the input. We will use a Turing machine that has special input tape on which it cannot write. And so then we don't count this tape for the space calculation. So I will make a necessary technical assumption just to make proofs easier. It's kind of ugly, but let's do it anyway. So I assume that the input head is always above the input, or at most the next cell after the input. So it can check where is the end, but it's not allowed to go further. Like we cut off the tape one cell after the input. So this is Turing machine. So here is the input tape. And then there is a certain number of work tapes, and we count the space on the work tapes. There also exists a Turing machine, for example, in log space transducer. So previous lecture, we briefly mentioned log space reduction. So then this is a machine that also has output. So it can happen that the input is linear, but also function needs to create linear output. And then we do the same thing. We create a special output tape. And here we have to do something special. In the output tape, once the output is written, it cannot be visited again anymore. We need this for combining reductions. And so there will be a one-way output tape. But okay, this is for the advanced results in circuit complexity. So you don't need to worry about reductions and output tape. Or if you want to make certain proofs really clean, you can use log space reduction. So about circuits. So when I prove that NC1 is an NL, so this was a bit of messy proof because you can construct a graph on the fly. You can break this proof in lemmas using log space reduction. Okay, but let's not speak about unnecessary things for the main materials. So now it's clear how we define space f of s, f of n, for f being less than linear. Okay, and now we are, let's look to the probability of directed reachability. So I will abbreviate. So input directed graph. So A is set of arcs, and then nodes S and T and V, and then the question. Exists path from S. Okay. So first question, is this solvable in logarithmic space? So this is just space log. So this is a very famous open question. Remarkably, for undirected graphs, this is indeed an L. So it's a result from less than 20 years ago by Reingold. So I haven't studied the proof yet. Well, I'm all, yeah. Okay. But this nature of computation, there was a chapter dedicated to this proof. But this problem is in NL. So how is non-deterministic space complexity defined? So this is the same. Here we have a non-deterministic Turing machine. And just, okay, it has two transition functions and it flips on, and every set it has uses one, and if element is in the set, then there is a way to choose a transition table so that it reaches accept state, the usual thing. Okay, so for certificate definition, that doesn't work with NL. Because a certificate is too long and you can create add a lot of things in it. It only works if you present a certificate on an addition. Okay, you could make such a proof, but the tricky part is, so what is tricky? Non-deterministic machine cannot store the choices it makes from the past. So when you build certificate, to store the choices, you need to make sure machine, once it chooses, it cannot remember what it chose a long time ago. So the idea is to have a special input tape on which the head goes in one direction. But okay, don't worry, you don't need to know this for anything. I'm just distracted by explaining you that certificate definition is tricky here. And it's a kind of source of mistakes. I mean, not in papers, but like while speaking with colleagues, there is always someone needed to remind about this. And if this person is missing, then there's some waste of time. Okay. Yes, so these are the two classes. Of course, it's open question whether NL equals L. Open question whether NL equals P. We do know that NL is different from NP by a non-deterministic version of space hierarchy theorem. Okay, so now let's go and prove that reachability is in space log squared.
Why is it clear that that the reachability problem is in NL?
Yeah, I forgot to say, yeah, that's why I defined this class. Yeah. So so just on input of the graph, we go to the node S, and then we guess one of the neighbors, we go to the next one, and so on. And after n steps, we see after at most n steps, we say reject. Unless before we saw the node T.
It's log of n because we need to store the
counter.
count.
Yeah, exactly. Yeah.
The count. Oh.
The counter. Well, the current node and also the counter we have to store.
Yeah.
Because in definition of decider, machine always needs to halve. And so in non-deterministic machine, we have the tree, and the runtime is defined as the longest branch. So we need to shut down the machine. Okay. So reachability is an NL. Okay, and now technique, but there was an exercise how to do this. You did something very closely with the ladder. So can you guess how you prove that reachability is in log squared? So algorithm is called middle first search. So it's yeah. Oh, you remember?
No, I just understand what you're saying. I don't remember. So we guess I think so we assume that that the size of the path is of size say k, and then we split the task by choosing a vertex v, and then we check that there is a path of size t divided by 2 between first vertex and the middle, and between the middle.
So it's divide and conquer. So to check, so we know that if there are n nodes, they are connected if and only if there is a path of length at most n. So then we recurse, we iterate over every node for a potential middle one, and then we check whether this node is connected in n over 2 steps to the first node and then the second node. And so what we're doing is we are reusing space. So this is why PSPACE is bigger than P, because time you cannot reuse, but space you can reuse. After you did half of a task, you reuse it. Okay, so let me write down the algorithm. I mean, it's a bit boring while I'm writing on the board, but then make sure you understand after I write it why it is in log squared.
It's pretty clear because like
the
log n is the first logarithm is depth of the recursion, and the second logarithm is just to store several variables.
Okay, but this algorithm is really important for the lecture, so I will write it down in detail because we will need to modify it for the two next results.
It's a pretty idea.
Yeah, sure. So let us have algorithm MFS, and so I will keep the graph fixed, and then it has two nodes and V and some length K, or let's call it L. And then, so first, if L is equal to 0, then we check output U equal V. Then if L equal 1, so then output, I should say return, because everyone knows Python. So output UV and A, whether UV is directed edge, and then otherwise we recurse. So for W in V, if MFS UW and MS WV, then return yes. And then if yes is not never happens, we return no. Well, so this is algorithm nicely written, and we need to store this carefully. So let us say one more time, why is it
MFS of U, V, and L divided by 2?
Yeah, oh, sorry. Yeah. L divided by 2, and we round up in 1.
And round down.
And the other we can round down. Thank you. But okay, we can round up in both cases. So now space analysis. So space analysis is space of so remember, if program crashes, you get recursion stack. It tells you how much space it tells you everything. Like this function is called with these arguments. It basically prints them all of the memory. I mean, there are no internal variables. So only except for W. So the only variables are U, V, L, and W in the program.
And L divided by 2 and 1.
Yeah. So
But
it's just
it's a constant number.
Yeah. So we have the variables in the call plus one more variable, but this one more variable is the same. So so the space is 3 times log. Well, anyway, order log of n, like 4 times log of n, and then we have to check recursion depth, which is also log of n, and so our space is log square. Okay, cool. So we have proven this thing. Now let's see why PSPACE equals NP-space. Can you tell me? Because it's direct consequence of previous question. So for this, we consider Turing machine and its configuration graph of Turing machine. So what do we know about number of nodes of configuration graph if machine runs in space, let's say f of n?
Runs in polynomial. If it runs in logarithmic space, then it runs in polynomial time.
Yeah. So number of configurations is at most 2 to the power order f of n. And so if machine runs in space f of n, so we have a language in space of f. Space f. So on input n, we will have that many configurations. So we build configuration graph and apply previous result. So we can make our life easy and make sure that the machine has at most one accepting configuration. So the machine runs, and afterwards we clean up the tape and bring the machine to the first cell. So then the machine accepts if and only if it reaches this special accept configuration with empty tape and machine on first cell. And so then we apply this problem here with initial configuration. So that contains the input word X. And here we have this unique accept configuration. And so here the number of, so the size of V is equal to number of config. And so this algorithm, it will run in space. So S runs in space the square of number of configurations, V squared, which is so it runs in size log square of V. Log square of V, which yeah, I know that there's some trouble with Zoom, so I mean with okay, so and log of V is order f of n, so we have order f squared of n. So if f is a polynomial, so if our language is in PSPACE, we choose f to be a polynomial, and we see that our algorithm runs in polynomial space. So we have proven that NP space is a subset of P space. And this is cool because clearly P space is a subset of NP space, so they're equal. Yes. And so more general, if a problem is solvable in space f of n, then it's solvable in space f squared of n. There is little subtlety here. There is a small, a minor problem when this claim. So
then should be at least logarithmic.
yeah, if yeah, okay, yeah, f is indeed logarithmic, but problem is actually slightly more general. And so let me write. So n space f of n space of f is a subset of deterministic space f squared. Okay. So you indeed want pathology. If we take like a square root of the logarithm, then the only languages are regular languages. And then oh no, then it also works. So it's not a counterexample if f is smaller than the logarithm. So there is nothing between space log and constant space. So yeah, it's not so obvious, and you need a proof for this. So so the problem solvable in constant space are automata, finite, they're regular languages.
Mm-hmm. Oh.
Okay. Yeah, sorry. So the problem is that to construct configuration space, we need to know the space bound. So we need a function that's space constructible. That means we can know the space bound, we can compute the space bound, but we do so and compute this using no more space than f of n. And so this actually, if f is more than linear, this is not really a problem because we can just try all strings and see what's the maximal space that's used. So every useful bound is space constructible if f is at least linear. But between linear and logarithmic, there is some problem. You can run in the problem. But the change of the algorithm is that you try increasing space bounds and you check whether your machine halts. So you do the middle first search, but when you run the search and you see that a halting machine goes out of its space, goes right at the limit you propose, then you stop the algorithm and retry it one more. And so you don't need to have the space bound. Okay, but I won't ask this for example. I will only ask about this thing. Okay, and now we are in the hardest part of our lecture. And time is going well. So, so the TQBF problem, TQBF stands for True Quantified Boolean Formula. So it's a generalization of tree set where we allow quantifiers in front of the formula. So, so let me say, imagine, let me give an example. Well, actually, sorry, TQBF, it doesn't need just any Boolean formula, not in tree set. But okay, in the exercise, you will see that doesn't matter. Both problems will be PSPACE complete. So, okay, let me first say what is, so imagine we have a formula with quantifiers. So there exists X for all Y, there exists Z, and all quantifiers are over single bits, 0 of 1. And then let me write the formula. So there is X or Y, and Y or not Z, and not Y or Z. Okay, and so you can understand this. Okay, it's 2 CNF formula. Okay, I need to read it by coincidence. It's not necessary, but not necessary CNF. Okay, and so this formula, you understand it. So here, quantifiers over bits, 0 or 1. So, of course, true or false? What do you think? Do you think it's true or you think it's false?
In this example.
Yeah. Okay, let me help you. Yeah.
So
what does this mean here?
Z should be so because the last clause should be true, then Y can be 1. Then okay, so Z should be true, and
yeah. So
and then
so just to help you.
Oh.
So these two are true if and only if Y is equal to Z. So now we can try to understand. So, okay, if you don't see it, let me explain. So there exists formula game. So there is a way to read this as a game. There is an exist player and a for all player. Exist player wants to make formula true. For all player wants to make it false. And so the players, they play according to the quantifiers. So here exist player starts and he has to say a bit. Then for all players says a bit, exist player says a bit, and if there are more and so on, if there are more. So here the question is, so the formula is true if exist player has a strategy to force 1 into the formula. So here we should think, what is strategy of exist player? So first he has to choose X. And it's clear how to choose X because X only appears positively. So he chooses X equal to 1. And then for all player will say whatever. And then the exist player will say the same value for Z. And then all the clauses are satisfied. This is formula game. So let's do another example. Let's flip the quantifiers. If we have for all, exist for all.
But the maybe all quantifiers exist, or all quantifiers are for all, or they like.
No. Now I wrote different quantifiers.
I mean,
and now
in the TQBF problem, the quantifiers are arbitrary or
arbitrary. They're part of. So the input is a formula of this form.
So they are not. It's not always can be interpreted as a game.
Yeah. So the input is quantified Boolean formula. So in TQBF.
I mean, if all the quantifiers are for all, or all the quantifiers exist, then
this is allowed.
There is no game.
Yeah, but tree set is special case SAT without the
Like
NF
always, yeah.
requirement. SAT is special case where all the quantifiers are exist. Okay, so it's clear that the equivalence with game, formula game, because we will use it later for generalized geography, we'll view formula as a game. Okay, so input is quantified Boolean formula. So that means every variable has a quantifier, and the question is a true. So this is TQBF. And now our big theorem is that so our what we aim to do, TQBF is PSPACE complete. And so I think you can guess what means PSPACE complete.
Any problem can be polynomial.
Yeah.
Space polar reduced to.
Yeah, exactly. So first condition, it must be in P-space. Second condition, every problem in P-space reduces to TQBF.
In polynomial space.
Yeah. So no, the reduction itself is polynomial time, not polynomial space.
Okay.
Because if we use polynomial space, then everything, then every function in P-space is complete by P-space reduction. Yeah. So that would be a stupid definition. Yeah. Just like every problem in P is polynomial time complete. Yeah. Okay. So two tasks. First, we need to understand why TQBF is in P-space. So again, to the two requirement in P-space and P-space hard, what means every problem in P-space goes to TQBF. Okay, so why in P-space? So when I say game, and you need to solve game by programming, what do? You
write a program that acts as a player.
Yeah, so you construct game tree.
Oh, okay. That's
more. So if you want to work in Google DeepMind, so they try to understand game tree of Go and all this nice game. But 8 years ago, you were still not watching the news. I forgot that now. How can you not know about Google DeepMind and AlphaGo? Okay, so you make game tree. That means that you look for the first player, you check all the moves. So here in our example, it's for all player. And then we look to all the moves of the exist player, and so on. And so we have the depth of the tree is number of quantifiers. And then in the leaf, there will be an answer, 1 or 2. Oh, sorry, and there is only 2 moves each time. So it's binary tree because all the players have 2 moves.
Then we check.
Yeah. And then we recurse. So we every node in the game is a position of the game, the configuration of the game. And so when we have here a node where for all has to play, then so we want to know if exist player has a winning strategy. So then we have to check whether to understand if this node is winning for exist. So let's call it 1 means formula is true. But let's also denote it 1 for exist player is winning. So here we know that if it's turn for all player, exist player loses because he will go to 0, the for all player. But then if we have a 1 here and here is the exist player, so then we know he can choose this. So this node becomes a 1. And if here is also an exist player, then You understand how you just need to traverse the tree that way first. And then you can solve using, so at every moment you have to store one branch. And since the size of the branch is polynomial, we conclude that, so the answer is given in polynomial space. So TQBF is in PSPACE. Okay. And now we have a harder task. We are given a problem and we need to make a reduction from this. So we have a problem in PSPACE and we need to build a reduction to a TQBF. So we are given an input, we have to produce a formula of this quantified Boolean formula. So let L be a language or not L. So let A be in PSPACE. Okay, so that means there exists a Turing machine that solves language A and uses polynomial space. So let's say M. Do we need many details? Okay, I will write some transition function start state runs in space P of M. So poly. This is polynomial. And now we have to so we want to make a reduction. So we are given an X, a word in the language over A, called sigma star. And we have to map it to a quantified Boolean formula that's true if and only if X is an A. Okay. And so what's the plan? The plan is that we will build configuration graph of machine A. So we just of machine M. And that's the only thing we have. So we have to use M. M is a Turing machine. So the only thing we can do is build configuration graph. And the only thing we know is that we can solve reachability efficiently. So our plan is to follow this program, but we need to evaluate this program using a Boolean formula. So we will make a formula that mimics this recursively. So how will this formula look like? So I can write here. So, well, there are three parts in our formula, right? And so let's call a formula psi1, psi2, psi3. Let's use okay. Let's use here. So let's make a formula. Let's construct it recursively. So well, let's call this formula psi L, and then when L is equal to 0 and 1, we can easily implement such formulas. Now we have to implement this part. And so the plan is to use recursion. So our formula psi L of U and V is equal to okay, so I just need to write this using psi L for smaller L. So this is our formula. It will make a quantifier over all nodes W. Node W we can represent as a binary vector. So if the graph has n node, a binary vector of length n, length n, that's just one hot encoding for machine learning people, just a unit vector and coordinate frame. So this is L of W, and then here we apply phi L over 2, round up.
So we represent. So there is
argument.
So there are order of number of nodes variables, not logarithmic. If you represent W as 1.5.
Nice. Oh, this is. Hold on. Why for a while?
No, not yeah, actually.
Yeah, this is a better idea. Thank you. There exists, and then when we have W over 2, let's round up to be consistent. U W and psi over 2 W. Okay, so that's our plan, and then we recurse. So we evaluate until we get W0 or W1. And so know that here there exists W, it's actually a shortcut for there exists W1, W exists W2, just and variables. Right? Okay, so does this work? Right, so I write down a formula here. Okay, so this you can write in binary. Phi 0 will check that all the bits of U and V are equal. So we know this trick there, we can build formula. So similar for L equal 1, we can just check for all A, whether we can just build a formula. So for it's
polynomial.
yeah, so for all pairs of nodes that are in A, we check whether U is equal to, so we build a long formula, but polynomial size. So phi 0, phi 1 we can build. And now, what do you think? Is this formula, is it polynomial size? So if you just expand the recursion.
Because
Yes, because it's there. Yeah. So the depth is logarithmic, but note we make two recursive calls. So we decrease the depth by half, but we multiply by 2 again because we have 2 evaluations. So
oh yeah.
so if we by the I see the so it's polynomial in L. In the depth that we have to search, but it's not polynomial in N.
It will be
because we need to choose L. And so the size of configuration graph is number of configurations. And this is only smaller than 2 to the power order of P of N. So it's not polynomial in N, it's exponential in N, this formula, because we have to choose this L. So we have to set L equal to an upper bound on the number of configurations. So failure, but we can rescue it.
Well, actually, it's of size order of size of.
So we have here
V in power of log of V, so it's 2 to the log squared.
Yeah, it's like times L poly N. Well, just but L is exponential. So this construction doesn't work. We rescue it as follows. So so here we have 2 times the W, and we can use formula only once by replacing. So we will make a quantifier over pairs of inputs. So what is the idea? So imagine I have a formula of this form. And so here is one formula, here is another formula. And I want to check that this formula implies this. So whenever this is true, then also this is true. So I want to say if something is true, then something else is true. Wait, I'm making a detour, but I will use it. So this is it's true if and only if not A of X or C of X. And so if A is true, this becomes false, and then this is true. So this is our plan. So now we will use a second quantifier over both arguments. And if argument is equal to either UW or equal to WV, then we check whether this is true. So this is how the formula looks like. Let's make some space. So phi, second attempt, is equal to, there exists W for all, and then for all A and B. We will have a formula that says AB equals UW, or I have no space. Oh wait, it's nicer. Let me write it on the bottom, but yeah, it's visible. Okay, new attempt. So there exists W for all AB. And then if AB is either UW or WV, and so for all choices of AB, such that AB is equal to, yeah, there exists W in noise, that's correct. So if AB equals to UV, or AB equals to VW. So if this is true, now I make some big brackets, then the formula should be true. Okay. Yeah. There exists W. Yeah. W. Yeah. And here W. So this is our formula. So for all AB, whenever AB, so we need to, do we have a W? So that for all AB, whenever AB is one of the two things, then formula AB holds. And this is a way to get rid of this and of the two recursive calls.
There is a problem with the rounding.
Oh yeah, sorry. So let's round up, and then we are good. So here we check if there is a path of length at most L over 2. L over 2, then there is at most a path of L over 2 plus 1 or plus 2 and so on. Okay, and so now we write down formula, and now we can recursively expand. So at each expansion, we divide L over 2, and we make the formula bigger by additive polynomial. So this is basically linear and the number of nodes. So then we recurse until we get phi 0 or phi 1. Okay. So now if we have X, we understand what will be our formula. So the reduction will be, I didn't write down the reduction, but it's clear how we will. So I need to reduce, so we get some X, and X will be mapped to psi. Here we will have our bound. So 2 to the power C of P of N, where C is constant, it depends on the machine. The start state will be the start configuration. Configuration that contains X on the tape, on the input tape. And then we have this accept configuration. So again, we assume machine has empty tape for accept, and so there is unique accept configuration. Yes, and that's our reduction. Where psi is a formula we built with this algorithm and psi 0, psi 1.
But then we have like the TQBF problem requires that we have all quantifiers first and then a formula, but in this expression there are quantifiers and there are also quantifiers like inside the formula. It's not really,
Good point.
That's really what we need.
Well, if first thing we make all variables different, and so imagine that there is for all inside here. For all X. So it's very easy we can just put X in the front, nothing happens. So if there are no name clashes, it doesn't matter where is the quantifier. So we just rename everything so that there are no clashes. So you're right. We built a formula using this one, and then we have many name clashes. So then we rename all variables and then simply put the variables in the front. It's a bit confusing because of this formula game. You say that, oh, here we have a nice order. But when the quantifiers are inside the formula, it's like the order is destroyed. But actually, if quantifiers on different variables appear in different places, the order doesn't matter in which for all players solves them. And so we just have to respect the scopes. Inside it, we can always move a variable to the front of the next scope. Yeah, it's a tricky point. So this is called normal form, I think, in logic lesson. If the score still exists. Yeah, so so now we've proven that TQBF is PSPACE complete, and TQBF is grandfather. I didn't hear the main saying this, but he probably would agree as grandfather of PSPACE complete problems.
TQBF actually looks like given a mathematical expression, is it true? So it actually can.
Yeah.
So if we prove that P equals P space, then we can like prove anything in mathematics in polynomial time.
Well, let's say a very discrete mathematics. And you need to be a bit careful because so here we have quantifiers over variables, but you can also have quantifiers over sets. Those that exist a finite set. And then so you can have sets of vectors, and then it's like exponential power inside the quantifier. Yeah. So it's like not everything.
Okay, yeah, on discrete.
Yeah. So there is a whole field of study. It's called descriptional complexity, like to capture the difficulty of problems using quantifiers, but of different type. Okay. Now I need to clean the board. Here. So last task is prove that generalized geography is PSPACE complete. So there exists a game that children play. So so you have to say a city, and then the other child says a city whose first letter is the same as the last letter of previous city. So like Moscow, Warsaw, Washington,
New York.
Yeah, New York. Okay, we can play it while cleaning the board and see how far we go. And don't need this anymore. And so we need to make but we will generalize this game. So it's a generalized undirected graph. So all the nodes, they are cities. And then one node is connected to another node if last letter of first is so we have a graph. And one node in the graph. So in this game, there is one special node where the game starts, where first player has to say something. And then there are, I tried to invent something clever for the sake of example. We have a game like this. And so every node can be used at most once. So there is kind of token here. And in turn, players move the token to another node.
Mm-hmm.
Or let's say copy the token to a new node. And then the first player who cannot move the token anymore loses. But there can be at most one token in every node. So here has first player winning strategy. No. So yeah, that's the game. Yeah. Otherwise, if in the game is Warsaw, you can repeat forever. So so here first player doesn't have a winning strategy. Let's think. So if he goes, there are only two moves. If he goes here, then second player will either go here or here. Oh wait, I should delete something. It's too hard. Okay, let's see if I delete this thing here. So first player moves, then second player goes here, and first player loses. So he will not go here. So if first player go here, then he wins. So this may be not interesting. So okay, so if he goes here, then
then the second player goes to there again and again.
Yeah, and then he loses. So here first player loses. Okay. So this is the generalized geography game. So I will abbreviate to write it faster. Input graph. So directed graph and start node S. And the question, let me write it properly. Okay, yeah. So question, first player has winning strategy. Okay, yeah. So please remember the game because I need to immediately erase to write down the reduction. So we will reduce TQBF to generalized geography. So I will start with a formula. Let's use the formula there. This formula.
Reduction from TQBF to this problem is particularly the vice versa.
Okay, so we start with formula. We need to produce graph.
Mm-hmm.
And so graph will have gadgets for variables and for clauses. in homework, you need to adapt this thing. Oh, sorry. Yeah. First, we have to say why it's in PSPACE. So we want to have the theorem that generalized geography is PSPACE complete. So why is it in PSPACE?
Because it can be reduced to TQBF problem, really. Well, because what does it mean that a player has a winning strategy like that? For there exists a move for first player, and then for every move for the second player, like and so on. Like we have order of n clauses where n is number of nodes in the graph, and then we write an expression that like checks that all moves are correct.
Yeah.
So yeah.
So only time reduces to TQBF. It's a new proof. Never considered this. So do you agree about this reduction? So there are two things now with this. It's a bit harder, this proof. So first he says, okay, let's move every move of every player, let's encode it as binary vector of length n. And then let's build a formula that says that no node is repeated. And so if a node is repeated, then corresponding player loses. And then we check whether after last move.
No, and then we check that every move is valid. Then yeah. There is an edge
in the graph.
Yeah. And that's it. That's all we need to check.
Every move is valid, and then we have to check that the first player wins. So we have to check that. So we need to allow also for not playing in the formula. Okay, no. So if second player has no move, then for any choice of his variables, the move is illegal, and yeah. So we check. Yeah, okay, I understand. Yeah. So this is polynomial time reduction because polynomially many things have to be checked.
Mm-hmm.
And so to check that's valid, we just have to check over sides of the history. So okay. Another way is just to write down the game tree, and the depth of the tree is polynomial in size. Mm-hmm. Because the game finishes after linear amount of moves.
Yeah, so it's n in n PSPACE.
Yeah.
So yeah, then
it's like quadratic space. Because to write down the whole game. To write down one branch, you can have large degree nodes.
Mm-hmm.
Almost. Yeah, you're right. Almost linear and log n strings. Okay. Yes. And now the reduction. So I will make a picture. So I need to make gadgets for variables and for clauses. I will draw them so you can look 5 minutes on your phone, and then we will understand everything. Like
once again,
Hamiltonian cycle. So
we can play the game.
Yeah.
The last city was New York.
Oh, that we need the other time. Are you watching something? It's from other teacher. Yeah, sorry, and now we have the cloud gadget. Okay, and maybe I need to insert something. Very interesting. Like we're almost done. So let me write the names of the clauses. X or Y. Here is Y or not. So let me explain what I just draw. So first, for every variable, we make such a gadget. And if the player alternates, then there is an extra line in between. So the idea is that the first player we associate to, I mixed up. Sorry, let's go back to the one that's true. First player is exist player. And so we have to make sure that first player has winning strategy if and only if the formula is true. Okay, so here is our formula. And then first player will choose the variable x, 0 or 1, with his move. And so the idea is that first player will follow the strategy and formula game to block the second player. So then after he plays, there are two moves he plays again. Sorry, there is no connection here. Oh, they go. No, this is not true. First play. Sorry, this is first move. It was correct.
Is it okay that like
So this is the for all player will do this catch. Then the exist player have forced moves. And now the for all player will choose one of these edges. So this is correct. And then there are two forced moves. So there's the turn of exist player who will go here. He will choose the move. And then so there is exist player, for all player, exist player. And now the for all player wants to prove that the formula is false. So he will choose the clause that is false. It's the idea of reduction. And if he is right, then okay, so what's the idea of blue connections? Variable clause gadget is connected to false literals. So two opposite literals. So for example, x is connected to x equals 0. So we connect to the bad value here. So y is connected to this one, but here not z is connected to the value of z, 1 here. So then that means that the node that was not chosen is still available for one more move. So if the clause is false, it means all literals are false. They will all go to nodes that were already used because they go to opposite values. So if x is chosen to be 1, then and y is chosen to be 1, then I missed yeah. Sorry, if x and y are chosen to be 0, then this clause is false. And then exist player has no move left here. And so here will be the turn of the for all player. And here is the turn of exist player. And if clause is false, he is blocked. So that's idea of reduction.
could you please repeat it? How does blue arrows work?
Yeah. So
so the players which one? They goes from the
let
top
me first
node.
say I did something bad. I mixed proof and construction because it's like tempting. The proof explains construction, but for you it's confusing because so in here every clause, every literal in the clause is connected to the value that makes it 0.
If there is. such a
Yeah. So x0. So so if it's a positive, sorry, let's say again, if the variable is positive, we connect it to the left side. And if it's negative, like not C here, we connect it to the right side here. So this is construction. So negative goes to the ones and positive goes to the zeros.
The formula in TQBF is a CNF formula. Or not?
Yes, it's okay. This is proof for CNF formula. Good point. I will explain the general case.
Okay.
It's easy to adapt, but let's first do
Okay,
CNF.
So it's a CNF, arbitrary CNF, not
Yeah.
free CNF.
Yeah.
Okay. Okay, now
So,
now it
but
makes
for
sense.
now, sorry. For now, let's use good point. So let's use CNF. Yeah, for now, and then it's. I promise you to explain the general case. Okay. And so we just need to remember x goes to the zero side, and not z. Negative literals go to the right side. Okay, and now the construction is clear for in the special case of CNFs. So let us consider the proof for CNF. So first, if there is a strategy of exists player that make formula true, then he will follow this strategy. He sees the move of the for all player and then reacts accordingly. Then this edge. So here we have for all. There are two forced moves. And then here for all player, since all clauses are, regardless of what for all player chooses, there will be one true literal. And this true literal, for example, if y is true, he can go to the opposite value by construction. He has one more move. And now this node is blocked because here we already used this edge. So this edge, so this node already disappeared. It's already used. So now the exists player, the for all player has no move left.
So if all the clauses are true, then then any move of the for all player will allow an exit player to make one more move, and then for all player will. Oh, get it.
Yeah, and now the opposite. So if for all player has strategy, so imagine that formula is false, then here second player has winning strategy for similar reason. So always when he comes here, always one of the clauses says all the things false, and then you go here.
Wait, but once again, if so this means that TQBF like the quantifiers should like be exists equal, and they should be like...
Okay, let me answer. So this is very special case with alternating quantifiers and formula in CNF. But this is not necessary. Why? Imagine we have two subsequent exist variables. Then we drop this extra edge so that the player doesn't that the player remains the same. And so here we have forced move. So here exists player goes. Then there is forced move for all. And if this edge doesn't exist, so we glue the nodes, then he plays again. So then this becomes exist player again. So just by dropping, so this is extra edge to change the player here between the gadgets. We can drop this edge in the construction. And so we have, or we can insert dummy variables to have always alternating. So it's other way,
Okay.
Then second question, what if it's not CNF? Well, then we just make a tree here. So we make a tree and maybe insert an extra node here. And so if the last move is an AND gate, and so what do we here? Here we basically have AND gates. And here we have ors. So we can continue and an or and an or. And when we end with an AND gate, we just add an extra node to the blue edges. So imagine that here we have, so our formula says x and y. What do we do? Then we just add one node here to change the player. And so formula is a tree, like parse tree of formula. And so we copy this tree here. And when the last operation was AND, then we just change the, remember that we can assume there are no negations. So we just have a tree where all the branches are AND and OR. So yeah, then we just build this tree, and whenever we end with an AND gate, we insert extra node to change player, and it's the same construction. But actually, so but actually it's not needed because there will be exercise to prove that TQBF, but here formulas in normal in 3CNF is also PSPACE complete. Okay, so that's it for this lecture, and we're just in time. Perfect timing. Despite the extra task, so it's very good. Yeah.
Less people, less questions, less time.
No, actually questions make everything go faster. Because the problem is that if I'm teaching, I forget to say something, but then people are silent for several minutes, and then I see everyone is sleeping, and then I need to think, oh, what is missing? I need to explain everything again, and the lecture takes longer. So there is a story like for research talk by Sasha Shen. And okay, I will keep the Zoom. And he says that a lecture or a research seminar, so there can be like a teacher that's like a locomotive, and it carries the train. And sometimes locomotive goes very fast, but when they have to go on a big hill, then wagons might be too heavy. And so the solution is that there is a second locomotive in the back of the train who pushes the wagons up. And so this is the same for lecture. So, but what is second locomotive in lecture? It's person who doesn't understand very much and all the time asks questions, and he pushes everyone over a mountain.